Welcome to The Explainer. Today, we're on a quest. We're going to try and understand the real heart of machine learning. How do you build a model that can actually, truly predict the future? Let's dive in. When you boil it all down, this is the one question that drives this entire field. It's not about magic, of course. It's about finding a smart, systematic way to learn from everything that's already happened to make a really good guess about what's coming next. So let's get this out of the clouds and make it real with a classic problem. Imagine you want to predict your sales. And what you know is how much you're spending on TV, radio, and newspaper ads. The relationship in math terms looks something like this. Sales is some function, we'll just call it f, of your ad budget. Our whole entire quest is to find the best possible version of that function f.
All right, so before we go searching for that function, we've got to make a choice. We have to choose our path. And in machine learning, there are really two fundamental paths you can go down. On one hand, you've got supervised learning. This is exactly like our sales problem. We have a clear target, our y, that's our sales numbers, and we want to predict it using our inputs, our x's. But then there's unsupervised learning. Here, there's no target at all. The goal is just to throw the data at the wall and see what sticks, Find some hidden structures or patterns. For our quest today, we're definitely taking that supervised path. We know exactly where we're trying to go.
But this path is not exactly a walk in the park. It's filled with dangers. On our journey for that perfect prediction, there are two big challenges. Two monsters, you could say, that we have to get around.
Okay, the first challenge has this super intimidating name, the curse of dimensionality. But honestly, the idea is pretty simple. The more features or dimensions you add to your data, the more that space just spreads out and becomes empty. It gets really, really hard to find data points that are actually close to each other. To really get this, picture this. Imagine your data is just a single line, right? One dimension. If we want to find the closest 10% of our data, we only have to look in this tiny, little, well-defined neighborhood. It's easy, it's local, it makes sense. But now, what happens if we add just one more dimension? All of a sudden, to grab that same 10% of the data, our neighborhood has to get huge. It's not really local anymore, is it? Now imagine this with hundreds of dimensions. Your so-called nearest neighbors could be miles away, which kind of breaks any method that relies on nearness to learn.
And this leads us to danger number 2, and it's a sneaky one. It's the trap of overfitting. This is what happens when you build a model that's so incredibly complex, so flexible, that it literally memorizes the data you trained it on, including all the random, meaningless noise. It looks perfect on paper, but it's totally an illusion. And this brings up a huge point. How do we even know if we're successful? Well, there's training error that tells you how well your model did on its homework, the data it's already seen. But what we really care about, the thing that matters, is test error. How well does it do on the final exam, with questions it's never ever seen before? An overfit model, it gets 100% on the homework, and then it completely fails the final. So, how do we do it? How do we steer between this curse of dimensionality and the trap of overfitting? Well, we need a map. And lucky for us, machine learning has one. It's called the bias-variance trade-off, and I'm telling you, this is the central idea for building anything useful.
First, let's talk about bias. The best way to think about bias is as your model's stubbornness. A model with high bias is just too simple. It makes these really strong, rigid assumptions, like trying to fit a perfectly straight line to a crazy, curvy pattern. It's just going to miss the point entirely. We also call this underfitting.
And on the flip side, you've got variance. And if bias is stubbornness, then variance, well, it's nervousness. A high variance model is just jumpy and oversensitive. It pays way too much attention to every single little data point, including all that random noise. And that is what leads you straight into the overfitting trap. And here is where it all comes together. This is a magic moment. When you see how these two forces, bias and variance, play against each other, you get this classic U-shaped curve. This is probably one of the most important charts in all of machine learning. See, on the left, simple models have high error, Because they're too biased. Way over on the right, super complex models also have high error because they've overfit. The entire goal of our whole quest is to find that beautiful sweet spot right at the bottom of the U. Believe it or not, you can actually write this whole idea out as a formula. The total error you can expect from your model is basically its bias squared plus its variance plus this other thing called irreducible error. That last part, that's just life. It's the random voids that exist in any real-world data. You can never, ever get rid of it. Our job is to find the perfect, delicate balance between the first two. So just think about that push and pull for a second. As you make your model more flexible, more complex, its bias is always going to go down, but its variance is always going to go up. That's the trade-off. You can't have your cake and eat it too. And it's this amazing tension that creates that signature U-shape in our test error. Okay, that's the theory. We have our map, the bias-variance trade-off. Now, how do we actually use it to finish our quest and build a fantastic predictive model? Well, in practice, it boils down to this really simple and incredibly powerful three-step playbook. Step 1, you split your data. You keep some of it to train your model, and you lock a separate chunk away for testing. Step 2, you build a bunch of different models, all along that spectrum from simple to complex. And finally, step 3, you unleash all of them on that unseen test data, and you just pick the winner, the one with the best score, the one that lands right at the bottom of that U. But there's one final twist in our quest, because sometimes getting the absolute highest score isn't the only thing that matters. There's another trade-off you got to think about: accuracy versus interpretability. A giant, super complex neural network might give you the most accurate predictions, sure. But if you have no idea why it's making those predictions, if it's just a black box, it might be useless or even dangerous. Sometimes a simpler model that's a tiny bit less accurate, but that you can actually understand and explain, well, that might be way more valuable. And that really brings us to our final thought. This quest for prediction, it's not just a technical puzzle, it's a strategic one. So I'll leave you with this to chew on. For your crystal ball, what's more important? A simple one that you can understand, or a perfectly accurate one that you can't? Thanks for joining us on The Explainer.